Hold your hand up and feel its weight. Nearly all of that weight is energy. Inside every proton in your body, 3 quarks are held together by the strong force, and the field doing the holding carries almost all of the mass you just felt. The quarks themselves account for about 1% of you. If you like taking one idea apart slowly, subscribe and stay with me. There is roughly 5 times more dark matter in the universe than ordinary matter, and nobody knows where its mass comes from. One answer is that it comes from the same place yours does, a second strong force, dark and confining, with quarks and gluons of its own, and a binding energy that sets its scale. Physicists call it dark QCD. We're going to build that idea from the ground, one step at a time, starting with a simpler question. What actually makes a proton heavy? Hold your hand out flat and let it hang there for a moment. Feel the small, steady pull on it. That pull is gravity acting on the mass of your hand, and the mass of your hand is the sum of the masses of everything inside it. Mostly protons and neutrons packed into the nuclei of carbon, oxygen, hydrogen, and nitrogen. So the question of what makes your hand heavy comes down to a much smaller question. What makes a proton heavy? The obvious answer is wrong. A proton is built from 3 quarks, 2 of a kind called up and 1 called down. Each quark has a mass given to it by the Higgs field, the same field that made news at the Large Hadron Collider in 2012. Add those 3 masses together and you get about 9 million electron volts of mass energy. The proton weighs 938 million electron volts. The parts account for 1% of the whole. 99% of the proton is missing from the ledger. Physicists use electron volts for mass because mass and energy are the same currency, which is what Albert Einstein was saying in 1905 when he wrote that energy equals mass times the speed of light squared. Most people read that equation in one direction, as a promise that a little matter can release a great deal of energy, which is what a nuclear reactor does. Read it the other way, and it says something stranger. Energy, if you can trap it somewhere and hold it still, weighs something. A box of light, if you could build one, would be heavier than an empty box. The proton is that box. Inside it, the 3 quarks are not sitting quietly. They are bound by the strong nuclear force, carried by particles called gluons, and that force does not weaken with distance the way gravity and electricity do. It stays taut. The field between the quarks is dense with energy, thick with gluons appearing and vanishing, and quark and antiquark pairs flickering in and out of existence too quickly to count. All of that churning energy is confined to a sphere about 1 femtometer across, a millionth of a billionth of a meter. Trapped there, it has weight. That weight is you. So when you feel your hand pull down against your shoulder, most of what you are feeling is not stuff. It is the strong force working and the energy it costs to keep working. Take a comparison and hold it for a moment. Imagine 2 people pulling on the ends of a rubber band, stretched tight. There is energy stored in that stretch. Now imagine the rubber band cannot ever be released, that it is stretched inside the proton forever, and that its stored energy has mass. Weigh the pair of people and their rubber band, and the rubber band's tension shows up on the scale. That is roughly the accounting inside a proton, and it is where you come from. The comparison breaks down almost immediately, and the way it breaks is the interesting part. A rubber band snaps if you pull hard enough, and its 2 halves go free. The strong force does not permit that. Pull 2 quarks apart and the energy in the field between them rises until it is cheaper for the universe to make a brand new quark and antiquark out of that energy than to let the old one separate. You never get a lone quark. You get 2 new particles, each with its quark still locked inside. Nobody has ever isolated a quark, and as far as anyone can tell, nobody ever will. Keep that fact close, because it is the seed of everything that follows. A force can generate mass out of its own effort, and it can hide its own constituents so thoroughly that they are never seen alone. Now hold both of those properties in mind and turn your attention outward to a cluster of galaxies photographed in the 1930s by a Swiss astronomer who kept a running list of people he considered fools. Fritz Zwicky moved from Bulgaria to Switzerland to California, arriving at the California Institute of Technology in 1925. He was brilliant, abrasive, and largely unloved by his colleagues, some of whom he liked to call spherical bastards, meaning that they were bastards when viewed from any angle. He also coined the term supernova, proposed neutron stars 2 years after the neutron was discovered, and suggested that galaxies could act as gravitational lenses. Nearly everything he suggested turned out to be right, and nearly nobody listened at the time. In 1933, he pointed his attention at the Coma cluster, a swarm of about 1,000 galaxies roughly 320 million light-years away in the constellation Coma Berenices. It hangs together as a group. Its galaxies orbit a common centre of mass, the way planets orbit the Sun, and Zwicky wanted to know how fast they were moving. He measured their speeds by their light, using the Doppler shift, the same effect that lowers the pitch of an ambulance siren as it passes you. Light from a galaxy receding faster is shifted redder. Light from one moving toward you shifts bluer. The spread of shifts across the cluster told him the spread of speeds. Then he did the accounting. A cluster of galaxies is held together by its own gravity, and gravity depends on mass. If the galaxies are moving too fast for the mass present, the cluster should have flown apart long ago, scattering its members into empty space. There is a formula for this, called the virial theorem, which relates the average kinetic energy of a bound system to the gravity holding it. Zwicky measured the speeds, applied the theorem, and read off the mass the cluster required. Then he estimated the mass the cluster actually had by counting its galaxies and assuming each one weighed roughly what its light suggested. The two numbers did not agree. They were not close. The Coma cluster needed something like 400 times more mass than its light accounted for by his first estimate. Later measurements brought that figure down considerably, because Zwicky's value for the expansion rate of the universe was off by a factor of several, and because most of the ordinary matter in a cluster turns out to sit in hot gas between the galaxies rather than in the galaxies themselves. But the gap never closed. It only shrank to a factor of 5 or 6 and then stopped shrinking. Zwicky wrote in German, and he called the missing ingredient dunkle Materie, dark matter. He meant it plainly. There was matter in the Coma cluster that did not shine, and there was a great deal of it, and it was the reason 1,000 galaxies had not scattered. Almost nobody followed up. The measurement was hard, the astronomer was difficult, and the conclusion sounded like an error. For 4 decades, the idea sat in the literature like a stone in a field. Other people walked past it. The Dutch astronomer Jan Oort had found something similar in 1932, looking at how stars bob up and down through the disk of our own galaxy, and had concluded there was more mass in the disk than he could see. He was more cautious about what it meant. Here is what matters about Zwicky's number for the story ahead. He did not measure a particle. He measured a discrepancy between motion and light. Every piece of evidence for dark matter since then has had that same shape. Something moves as though gravity is stronger than the visible matter can explain. The evidence is not a detection. It is a bookkeeping error the size of the universe, and it has appeared independently in every place anyone has looked. The next place anyone looked carefully was inside a single spiral galaxy, 40 years later, through a telescope in Arizona. Vera Rubin wanted to work on something nobody else was working on. She had learned, by the 1960s, that the crowded and glamorous problems in astronomy came with crowds attached, and that the crowds had not always been kind to her. She had been told as an undergraduate that she could not apply to Princeton, which did not admit women to its graduate astronomy program until 1975. She had presented a thesis result at a meeting of the American Astronomical Society at the age of 22, 6 weeks after giving birth, and watched it get dismissed. So she chose a quiet problem, one she expected to be tedious. She would measure how fast stars orbit in the outer parts of spiral galaxies. Her instrument was built by Kent Ford, an instrument maker at the Carnegie Institution. It was an image tube spectrograph, and it was extraordinary for its time, amplifying faint light so that a spectrum of a galaxy's dim outskirts could be captured in hours rather than nights. Rubin and Ford began with Andromeda, our nearest large neighbour, 2.5 million light-years away, and worked outward through dozens of other spirals. The expectation was simple, and it came straight from the solar system. Mercury orbits the Sun at about 47 kilometers per second. Neptune, 30 times farther out, crawls at 5. The Sun holds nearly all the mass, so gravity weakens with distance, and the outer planets move slowly. A spiral galaxy concentrates its light in a bright central bulge, so past that bulge the stars should behave like Neptune. Their orbital speed should fall off as you go outward. They do not. Rubin and Ford found that stars near the visible edge of a galaxy orbit at essentially the same speed as stars well inside it, 200 kilometers per second or so, held flat across tens of thousands of light-years. The graph of speed against radius, which should curve downward, runs level to the last measurable point, and then keeps running level. Radio astronomers tracking hydrogen gas beyond the stars, among them Albert Bosma and Morton Roberts, found the flat curve continuing far past where the light gives out. The only way to keep a distant star moving that fast is to keep piling mass inside its orbit as the orbit grows. Every galaxy Rubin measured was sitting inside a vast, roughly spherical halo of something that had mass and gave off no light. The halo extends perhaps 10 times farther than the stars and outweighs them several times over. The bright spiral you see in a photograph is a small luminous decoration at the centre of a much larger invisible object. Rubin was careful and unhurried about the conclusion. She published rotation curves for 21 galaxies, then 60, then more, and by the early 1980s the flat rotation curve had become one of the most reliably reproduced results in astronomy. She never claimed to know what the halo was made of. She said the observations required mass where there was no light, and she let that stand. Notice what has changed since Zwicky. He had one cluster and a contested formula. Rubin had ordinary galaxies, one after another, each independently demanding the same missing mass in the same rough proportion. The discrepancy had stopped being an anomaly and had become a property of galaxies. Both measurements share one weakness. Each infers mass from the motion of visible things, so each depends on assuming that gravity behaves as Isaac Newton and Albert Einstein described. To press further, you would want to weigh a galaxy without watching anything orbit it at all, and to do that you need to watch what its gravity does to light passing by. In 1936, a Czech engineer named Rudy Mandl talked his way into Albert Einstein's office in Princeton, and asked whether a star's gravity could bend the light of a star behind it into a ring. Einstein worked it out, published a short paper in Science, and told the editor privately that the calculation was of little value, but that the man had asked him to write it. He thought the alignment required would be too rare to matter, and the ring too small to see. He was right about stars and wrong about scale. Gravity bends light because mass curves the space light travels through, a prediction confirmed in 1919 when Arthur Eddington photographed stars near the eclipsed Sun and found them displaced. Put a mass as large as a galaxy cluster in the way, and the bending becomes obvious. In 1979, Dennis Walsh and his colleagues found two quasars sitting close together in the sky, with identical spectra, and realized they were looking at one quasar twice. Its light split around an intervening galaxy. Since then, astronomers have found rings, arcs, and multiple images by the thousand. This gives you a scale. Photograph a cluster of galaxies and you will see the background galaxies behind it stretched into thin arcs, smeared around the cluster like reflections in a warped window. The amount of stretching depends only on the mass in the way and where it sits. You do not need to know what the mass is made of, whether it is moving, whether it shines, or whether it feels any force except gravity. You measure the distortion, and you get a map of mass. This technique, gravitational lensing, weighs clusters, and it agrees with Zwicky. Most of the mass is not the galaxies and not the gas. Then, in 2006, Douglas Clow and his collaborators published an image of a system called 1E0657 Theix, better known as the Bullet Cluster. It is two galaxy clusters that have passed through each other, one driving through the other like a bullet at several thousand kilometers per second. The collision happened long enough ago that the wreckage has separated. Here is what happened during that crossing. The galaxies in each cluster are small and far apart, so they sailed past one another almost untouched, the way two swarms of gnats can pass through each other without a single collision. The hot gas, which is most of the ordinary matter by mass and glows brilliantly in X-rays, could not do that. Gas hits gas. It piled up, slowed down, and stayed behind in the middle, where the Chandra X-ray Observatory photographed it as two glowing, shock-heated clouds. So Clow made two maps of the same patch of sky. One was the X-ray map, showing where the ordinary matter is. The other was a lensing map showing where the mass is, drawn from the shapes of distant galaxies seen through the wreckage. If the mass were the gas, the two maps would lie on top of each other. They do not. The mass sits in two lumps out ahead, tracking the galaxies, while the gas lies between them. Most of the mass in each cluster went straight through the collision without slowing, as though the other cluster were not there. That result does two things at once. It shows that the mass is not the ordinary matter, since the two are physically separated and now sit in different places. And it shows that the mass barely interacts with itself, because a substance that collided the way gas collides would have piled up in the middle too. The bullet cluster is the closest thing to a direct photograph of dark matter that anyone has. It shows a substance that has mass, ignores light, ignores gas, and mostly ignores itself. What it does not show is when this substance arrived, or whether it was there before there were any galaxies at all. For that you have to look at light that started travelling before a single star existed. In 1964, at Bell Labs in Holmdel, New Jersey, Arno Penzias and Robert Wilson had a horn-shaped antenna and a hiss they could not get rid of. It came from every direction of the sky equally, day and night, summer and winter. They cleaned out a pair of nesting pigeons and scrubbed the droppings, a detail Penzias later described with some resignation, and the hiss remained. 37 miles away at Princeton, a group led by Robert Dick was building an antenna to look for exactly that signal. The hiss is the cosmic microwave background, and it is the oldest light there is. For the first 380,000 years, the universe was hot enough that atoms could not hold together. Electrons roamed free, and free electrons scatter light, so the universe was an opaque glowing fog. Then it cooled below about 3,000 degrees, electrons settled onto protons, hydrogen formed, and the fog cleared all at once. The light released at that moment has been travelling ever since, stretched by the expansion of space from orange glow to microwave, cooled to 2.7 degrees above absolute zero. It arrives from every direction because that moment happened everywhere. The light is not perfectly smooth. It carries temperature ripples of about 1 part in 100,000, first mapped by the COBE satellite in 1992, then far more finely by WMAP and by the Planck satellite, which released its final results in 2018. Those ripples are a photograph of the fog at the instant it cleared, and they are the single richest measurement in cosmology. Here is what they record. Before recombination, ordinary matter and light were locked together in one fluid. Gravity pulled that fluid into dense spots. Radiation pressure pushed back. The fluid oscillated, compressing and rebounding, and it did so as sound waves, real acoustic waves in a real medium, with a real speed of sound. When the fog cleared, the waves froze in place. Their pattern is written across the sky as a series of characteristic spot sizes, and when you plot how much ripple there is at each angular scale, you get a set of peaks. Now the crucial part. Ordinary matter feels the radiation pressure. Dark matter does not, because it does not interact with light. So dark matter fell into the dense spots and simply stayed, deepening the gravitational wells without ever bouncing back out. That difference shows up in the peaks. Compression peaks get boosted relative to rebound peaks, and the exact ratio between the second and third peaks measures how much of the matter felt the pressure and how much did not. The answer is precise. About 5% of the total energy content of the universe is ordinary matter, made of protons and neutrons. About 27% is matter that does not feel light. The remaining 68% is dark energy, a separate mystery driving the expansion faster and not our subject here. The cosmic microwave background adds 3 facts that no cluster measurement could. Dark matter existed before the first star formed, so it cannot be dim stars or cold planets or anything made after stars. It was moving slowly when structure began forming, because fast-moving particles would have streamed out of small clumps and erased them, and the small clumps are there. Physicists call this cold, dark matter, and it does not scatter light even a little, at any wavelength, at any epoch. Cold, present at the beginning, blind to light, and 5.5 times as abundant as everything you have ever touched. That ratio is not a rounding error, and it is not a coincidence you can wave away. It sits in the data with 3 significant figures, and it deserves a chapter of its own. Take the Planck numbers and put them side by side. Ordinary matter, everything made of protons and neutrons, comes to about 4.9% of the universe's energy budget. Dark matter comes to about 26.8%. Divide one by the other and you get 5.4. That number should bother you, and to see why, you have to know how physicists think each kind of matter got here. Ordinary matter is left over from an accident. In the early universe, matter and antimatter were made in nearly equal amounts, and matter and antimatter annihilate on contact, converting themselves entirely into light. Had the amounts been exactly equal, the universe would now contain photons and nothing else. There was a slight excess of matter, roughly 1 extra proton for every billion proton-antiproton pairs. Everything annihilated, that 1 part in a billion survived, and it is the stars, the planets, the oceans, and you. The mechanism that produced the imbalance is unknown. Andrei Sakharov laid out in 1967 the 3 conditions any such mechanism must satisfy, and the search for one that works is still open. Whatever it was, it set the amount of ordinary matter by an asymmetry, a tiny surplus of something over its opposite. Dark matter, in the standard picture, got here a completely different way. A stable particle, produced abundantly in the hot early universe, annihilating with its own antiparticle until the universe expanded enough that the particles could no longer find each other. At that point, the annihilation stops, and whatever is left is frozen in. The abundance you end up with depends on how strongly the particle annihilated, not on any asymmetry. Physicists call this thermal freeze-out, and the amount it leaves behind depends on an interaction strength, not on a leftover surplus. 2 mechanisms with nothing in common. One depends on an unknown asymmetry, the other on an annihilation rate. There is no reason those 2 outcomes should land within a factor of 6 of each other. They could have differed by a factor of 1,000 or 1,000,000. The universe could easily have been mostly dark matter with a whisper of ordinary matter, or the reverse. Instead, it produced 2 substances in roughly comparable amounts, and the comparability is what makes galaxies as they are. Ordinary matter cooling and falling into dark matter halos and forming stars in the wells that dark matter dug. Physicists have a name for the discomfort. They call it a coincidence problem, and they treat it as a clue rather than a curiosity, because in the past such coincidences have paid out. When the abundances of helium, deuterium and lithium all turned out to match a single early temperature history, that was not luck. It was a signature of the mechanism that produced them. So a suspicion forms. If dark matter and ordinary matter were made in comparable amounts, perhaps they were made by related mechanisms. Perhaps dark matter also owes its abundance to an asymmetry, a surplus of dark particles over dark antiparticles, tied by some shared process to the surplus that gave us protons. And if the 2 number densities are related, then the mass ratio of 5.4 tells you something about the mass of the dark particle. A rough version of the argument suggests it should be about 5 times the mass of a proton, a few billion electron volts, which is a comfortable and specific place to look. That line of reasoning has a name and a chapter waiting for it. Set it down for now. The community spent most of 30 years pursuing a different idea, one whose own numerical coincidence was even more seductive, and the story of how that search went is the reason anyone started looking at the strong force in the first place. Suppose the dark matter is a heavy, stable particle that was once in thermal equilibrium with everything else, and suppose it annihilates through the weak nuclear force, the force behind radioactive beta decay. Turn the crank on the freeze-out calculation. The answer depends on the annihilation cross-section, which depends on the coupling strength and the particle's mass, and if you put in the weak coupling and a mass somewhere between about 100 and 1,000 times the protons, out comes a relic abundance close to 27% of the universe. Nobody arranged that. It falls out. Physicists named it the WIMP miracle for weakly interacting massive particle, and for 3 decades it was the most attractive idea in the field. Supersymmetry, a theoretical framework proposed for entirely separate reasons in the 1970s, happened to predict exactly such a particle. The lightest neutralino, stable and neutral and weighing a few hundred times the proton. 2 independent lines of reasoning, one cosmological and one from particle theory, pointed at the same object. The case looked strong enough that a generation of physicists organised their careers around it. If the WIMP annihilates with ordinary matter's particles, then run the same interaction backwards, and a WIMP passing through a lump of ordinary matter should occasionally strike a nucleus and make it recoil. That recoil is small, a few thousand electron volts of energy, but it is not zero, and the galactic halo we live inside would be blowing through any detector at about 230 kilometers per second. So they built detectors. They put them deep underground to escape cosmic rays, in the Homestake mine, under Gran Sasso Mountain in Italy, in a nickel mine in Sudbury, in Bulbi, in Jinping. They filled them with germanium crystals, then with liquid xenon and liquid argon, chilled and shielded and monitored for any flash of light or ionization from a recoiling nucleus. The experiments took names like CDMS, Xenon, Eloaki, Panda X, Dia, and each new generation grew by roughly a factor of 10 in sensitivity. They found nothing, not a hint. Xenon 1T ran a ton of liquid xenon for a year and reported no signal. Its successor, Xenon T, and the LX Zeppelin experiment in South Dakota run several tons and have reported no signal. Over roughly 30 years, the exclusion curves have descended by more than 5 orders of magnitude, sweeping through the region where supersymmetry most naturally lived, and then well below it. The Large Hadron Collider spent the same years looking for supersymmetric particles in its collisions and found none. The detectors are now approaching a floor they cannot pass. Neutrinos from the sun and from cosmic rays hitting the atmosphere produce nuclear recoils that look almost exactly like a WIMP signal, and below a certain sensitivity that background becomes irreducible. Physicists call it the neutrino fog. It is a hard limit, and the WIMP search is running into it. None of this proves the WIMP does not exist. The parameter space is not fully closed, and careful people continue to look. But something changed in the field, and it changed slowly, the way these things do. The miracle stopped feeling like a miracle. The coincidence that made the weak scale look special began to look like the kind of coincidence that happens when you have enough free parameters to arrange one. And a question that had been in the background stepped forward. The WIMP idea took the dark matter's mass as an input, a number you dial in set by a Higgs coupling you never explain. But we know of one place in nature where a mass scale is not dialed in at all, where it generates itself out of a force. It made you. It made your hand. The question is whether it could make something else, somewhere we cannot see, and to ask that question properly you first have to understand what the strong force actually is. Every force in nature is bookkeeping about a charge. Gravity keeps books on mass and energy. Electricity keeps books on electric charge. of which there is one kind coming in two signs, positive and negative. The strong force keeps books on a charge that comes in three kinds, and by an old joke that stuck, the three kinds are called red, green, and blue. They have nothing to do with light. The names were chosen because three of them combine into something neutral, the way three coloured lights combine into white. The reason there are three is empirical and slightly desperate. In the early 1960s, a particle called the omega minus was predicted to exist, made of three strange quarks, all identical, all in the same state of motion, all spinning the same way. That is forbidden. The Pauli exclusion principle says two identical particles of that class cannot share a state, and here were three. Oscar Greenberg and separately Mu Young Han and Yoichiro Nambu proposed the fix. The three quarks are not identical after all. Each carries a different value of a hidden charge with three possible settings. The exclusion principle is satisfied, and the price is a new property of matter that nobody had ever seen. The mathematics for such a force already existed, and it had been sitting in a drawer considered useless. In 1954, at Brookhaven National Laboratory, Chen-Ning Yang and Robert Mills wrote down what happens when you take the structure that underlies electromagnetism and demand that the charge be something with more than one component, something that can be rotated among its settings independently at each point in space. The theory that results is fixed almost entirely by that demand. You get force-carrying particles, and you get an equation for how they behave, and you get no freedom to choose. Yang presented the work at Princeton, and Wolfgang Pauli, who had thought along similar lines and abandoned it, interrupted him from the audience to ask what mass the new force-carrying particle had. Yang said he did not know. Pauli pressed. Yang sat down. The theory seemed to demand massless carriers, which would produce a long-range force like electromagnetism, and no such force existed. The paper was published anyway and waited 19 years. What Yang and Mills had actually written was the strong force, and the objection contained the answer. The carriers are massless. They are called gluons, and there are 8 of them. Here is the property that separates this force from every other. A photon, the carrier of electromagnetism, carries no electric charge. Light does not shine on light. Two beams cross without noticing each other. A gluon carries colour charge. It carries one colour and one anti-colour at once, so gluons pull on gluons. The force acts on its own carriers. Take an ordinary picture and then break it. Think of the electric field around a proton as a set of lines spreading outward in all directions, thinning as they go, the pull weakening with the square of the distance. That is what field lines do when they ignore each other. Now let the lines attract one another. They stop spreading. They gather into a narrow bundle, and a bundle that does not thin with distance is a force that does not weaken with distance. That single feature, the force acting on itself, produces everything strange about the strong interaction, including its habit of turning energy into mass and its refusal to let a quark travel alone. To see how it was pieced together, go back a few years before the colour charge was invented, where nobody knew there were quarks at all, and the accelerators were producing new particles faster than anyone could name them. By the late 1950s, the accelerators had gotten out of hand. Cosmic ray studies and machines at Brookhaven and Berkeley kept coughing up new particles, dozens of them, each heavier than the proton, and each dying in a fraction of a microsecond. The pion, the kaon, the lambda, the sigma, the psi, the rho, the delta. Enrico Fermi told a student that if he could remember the names of all these particles, he would have been a botanist. Willis Lamb joked at his Nobel banquet that the discoverer of a new particle used to be rewarded with a prize and should now be fined $10,000. Murray Gell-Mann at Caltech was the sort of person who noticed patterns and did not let them go. He was a prodigy who had entered Yale at 15, a linguist and birdwatcher, and by reputation a difficult colleague who was nearly always right. He began sorting the particles by their properties, plotting them on charts by electric charge, and by a quantity he named strangeness, invented to explain why certain particles were produced quickly and decayed slowly. The particles fell into geometric patterns, 8 here, 10 there. He called the scheme the Eightfold Way, borrowing a phrase from Buddhism, mostly as a joke. Yuval Ne'eman, an Israeli military officer studying physics in London, found the same pattern independently in the same year. The mathematics behind it is the symmetry group called SU3, and it was already known to mathematicians. The scheme had a hole. One of the patterns was a triangle of 10 particles, and only 9 were known. Gell-Mann stood up at a conference at CERN in 1962 and predicted the 10th, giving its charge, its strangeness, and its mass. 2 years later, at Brookhaven, a bubble chamber photograph showed the omega minus at the mass he had named. That was not a fit. That was a prediction, and it turned the pattern into physics. Then Gell-Mann asked what would generate such patterns, and found that they arise naturally if all these particles are built from 3 more basic objects. He called them quarks, taking the word from a line in Finnegan's Wake by James Joyce and giving it the sound of a duck's call. George Zweig, working at CERN at the same time and quite independently, reached the same construction and called his objects aces. Zweig's paper was never accepted by a journal. The quarks had a problem that made them nearly unpublishable. Their electric charges had to be 2/3 and negative 1/3 of the electron's charge. Nobody had ever measured a fractional charge, and everybody had measured charge very carefully. Robert Millikan's oil drop experiment had established that charge comes in whole units. Gell-Mann hedged carefully in print, calling the quarks mathematical devices and suggesting the fractional charges might mean they could never be isolated. He was half hedging and half right, which is a strange place to be. The quarks are real. Deep inelastic scattering experiments at the Stanford Linear Accelerator Center in 1968, led by Jerome Friedman, Henry Kendall, and Richard Taylor, fired electrons hard into protons and found them bouncing off small hard objects inside, 3 of them, exactly as Gell-Mann's arithmetic required. Richard Feynman, who preferred to stay agnostic about names, called the hard things partons. And the quarks are also never isolated. Nobody has caught one. So the pattern was right, the constituents were real, and yet the constituents could not be extracted, and nobody understood why. The answer would come from a discovery that runs against every instinct you have about how forces behave, made by 2 graduate students and their advisors in the same season of 1973. Push 2 magnets together and the force between them grows. Move them apart and it fades. Every force anyone had ever met behaved that way. Get closer, feel more. Move away, feel less. Electromagnetism does it. Gravity does it. The weak force does it. It is not a law so much as a habit of the universe, and by 1970 it looked unbreakable. The slack scattering results broke it. When electrons were fired into protons at high enough energy, they scattered as though the objects inside the proton were free. Not bound, not tugged at, free. James Bjorken had predicted this behaviour mathematically before it was seen, a property called scaling, and the data obeyed. But if quarks rattle around loose inside a proton, why can you not shake one out? The 2 facts contradicted each other. Something inside the proton was holding the quarks with unbreakable strength, and simultaneously letting them float untouched. The resolution came in 1973. David Gross, a young professor at Princeton, set his graduate student Frank Wilczek the task of proving that no quantum field theory could behave that way. Gross expected the calculation to close the door. It was a hard calculation, involving how the strength of a force changes when you probe it at different distances, a behaviour physicists call running. Wilczek and Gross ran it for the Yang-Mills theory. At Harvard, David Politzer, also a graduate student, ran the same calculation alone. Both got the same answer, and both got the sign backwards from what anybody expected. The strong force weakens at short distance. Push 2 quarks close together and they barely feel each other. Let them drift apart and the force grows without limit. Physicists call the short distance behaviour asymptotic freedom, and it is the reason quarks look free inside a proton and are still trapped there. The 3 papers appeared in the same issue of Physical Review Letters. The 3 men shared the Nobel Prize in 2004. The mechanism is the self-interaction from 2 chapters ago, and it inverts the ordinary story. In electromagnetism, an electron sitting in the vacuum is surrounded by a fizz of particle pairs popping in and out of existence, and those pairs orient themselves to partly cancel its charge, the way a molecule of water turns to shield an ion dissolved in it. Get closer, and you push inside the shield and the charge looks bigger. That is screening, and every force does it. The strong force does it too. But gluons carry colour, so gluon pairs in the vacuum also fizz, and gluons do not shield a colour charge. They smear it outward, spreading it into the surrounding space. Get closer and you are inside less of the smear, so the charge looks smaller. The 2 effects fight. The quark pairs screen, the gluons anti-screen, and which one wins depends on arithmetic, on the number of colours versus the number of quark flavours. With 3 colours and 6 flavours, anti-screening wins comfortably. If there were 17 flavours of quark, it would not, and the world would be entirely different. So the strong force has a distance dial. At distances much smaller than a proton, probed by very high energy collisions, the coupling is weak enough that physicists can calculate with pencil and paper. That is why the theory, which now had a name, quantum chromodynamics, could be tested at all. At distances comparable to a proton, the coupling grows to about 1, and every approximation collapses, which leaves the other half of the puzzle standing. The force grows with distance and it does not stop growing. So what actually happens if you take hold of a quark and pull? Take hold of a quark and pull. This is a thought experiment, and it is also, roughly, what happens inside a particle accelerator every time an electron and a positron annihilate into a quark and an antiquark flying apart at nearly the speed of light. The field between them does not spread out. Because gluons attract gluons, the colour field collapses into a narrow tube running from one quark to the other, about 1 femtometer across, like a taut string. The energy stored in that tube grows in proportion to its length. Pull the quarks 1 femtometer apart and you have stored roughly 1 billion electron volts of energy in the string. Pull them 2 femtometers and you have stored 2 billion. The number is called the string tension, and it is nearly 1 billion electron volts per femtometer, a fact measured in a dozen ways. Keep pulling, and the string keeps storing energy, and at some point the universe finds a cheaper arrangement. 1 billion electron volts is more than enough to make a quark and an antiquark out of nothing, since a light quark costs only a few million. So the string snaps in the middle, and a new quark-antiquark pair appears at the broken ends. Instead of 2 separated quarks, you now have 2 mesons, each with its quark and antiquark bound close. Pull harder, and you make more mesons. The energy you put in becomes matter, and the matter arranges itself so that no colour charge is ever exposed. This is called confinement, and it is why you have never seen a quark. It is also visible in a sense. When a quark flies out of a collision at the Large Hadron Collider, it drags a colour string behind it. That string breaks over and over, and the debris arrives at the detectors as a tight spray of ordinary particles all moving in nearly the same direction. Physicists call the spray a jet. Every jet you see in a collision photograph is the funeral of a single quark, the record of a string that snapped repeatedly on its way out. Compare it to pulling apart 2 magnets, and then watch the comparison break. Break a bar magnet in half, and you do not get a north pole and a south pole. You get 2 smaller magnets, each with both poles. That is a real and useful echo of confinement, and it fails in one important way. The magnet breaks because of how the atoms inside are arranged, and there is nothing energetic about it. The colour string breaks because the energy in the field has become large enough to manufacture new particles. It is not rearrangement. It is creation, paid for out of the field. There is a related fact that is easy to state and appallingly hard to prove. The theory of quarks and gluons contains no massless particles in its list of observable states, even though the gluon itself has no mass. Everything the theory produces, every meson and baryon, has a minimum energy. This is called the mass gap, and it is one of the 7 Millennium Prize problems posed by the Clay Mathematics Institute, with $1 million offered for a proof. No one has claimed it. The most successful theory in the history of physics has never been shown, with mathematical rigour, to do the thing it plainly does. But if you cannot prove it, you can still compute it. And when physicists do compute it, using a machine and a lattice of imaginary points in space, the proton's mass falls out of the calculation with no quark masses worth speaking of. That is the calculation that puts a number on the first chapter, and it deserves to be told carefully. In 1974, Kenneth Wilson wrote down a version of quantum chromodynamics that lives on a grid. Space and time become a lattice of points, a few tenths of a femtometer apart. Quarks sit on the points. Gluons live on the links between them. The continuous theory becomes a finite problem with a finite number of variables, and a finite problem can be handed to a computer. The computer does not solve the theory, it samples it. Quantum field theory says that a proton is not one configuration of quarks and gluons, but every possible configuration at once, each weighted by a probability. Lattice quantum chromodynamics generates a large number of gluon field configurations drawn from that probability distribution, then measures what it wants to know in each, and averages. The technique is called Monte Carlo, after the casino, and it eats supercomputer time by the millions of processor hours. The calculation you want is this. Give the machine nothing but the theory itself. Hand it 3 numbers for the masses of the up, down, and strange quarks, and 1 number setting the overall scale, and nothing else. No proton, no neutron, no measured hadron masses. Then ask it what a proton weighs. In 2008, a collaboration led by Zoltán Fodor and Stefan Dürr, working across Wuppertal, Budapest and Marseille, published the result in Science. They computed the masses of the light hadrons from first principles, the proton, the neutron, the pion, the kaon, the omega minus that Gell-Mann had predicted, the whole family. The numbers agreed with the measured masses to within a few percent, which was the size of their error bars. Sit with what that means. 938 million electron volts of proton, and the quark masses put in by hand contribute about 9 of them. The other 929 million electron volts were generated by the machine out of the dynamics of the field, out of gluons pulling on gluons, out of the churn of virtual pairs, out of confinement itself. The mass came from the force. There is a way to see it that makes it feel less like magic. Confinement traps the quarks in a region about 1 femtometer across. Quantum mechanics says that a particle confined to a small region cannot sit still. Its momentum becomes uncertain by an amount inversely proportional to the size of the box, which is Werner Heisenberg's uncertainty principle, applied without any subtlety at all. Squeeze a nearly massless quark into a femtometer, and it acquires a momentum of a few hundred million electron volts, and therefore an energy of a few hundred million electron volts, because a nearly massless thing carries energy equal to its momentum times the speed of light. 3 quarks, a few hundred million electron volts each, plus the energy in the gluon field holding the box shut. You're in the right neighbourhood before you've done anything careful. The mass of ordinary matter is the price of keeping quarks in a box, and the strong force builds the box. Take away the Higgs field entirely, so that quarks weigh nothing at all, and the proton would still weigh about 98% of what it does. You would still be heavy. Now push on 1 loose thread. The size of the box came from somewhere. The strong force gets stronger with distance, and it reaches strength 1 at a particular distance, and that distance set the femtometer, which set the momentum, which set the mass. So there is a scale hiding in quantum chromodynamics, a length and an energy that the theory produces from itself. Nobody put it there. It is worth understanding exactly where it came from, because that is the trick that a dark sector would have to repeat. Write down the theory of the strong force and look for a mass in it. Take the quark masses out, Set them all to 0 and look again. There is nothing. The equation contains a number that says how strongly gluons couple to colour charge, and that number is dimensionless, a bare ratio with no units attached. There is no length in the theory. There is no energy. There is nothing that could tell you how big a proton is or what it should weigh, and yet the proton has a size and a weight, and they are not arbitrary. This is one of the deepest and least advertised facts in physics, and it has a name that sounds like a bad translation. Dimensional transmutation. Here is how it works. The coupling is not a fixed number. It runs, as Gross, Wilczek, and Politzer showed, changing its value depending on the distance at which you measure it. Probe a proton with a very high energy electron, which is to say look at it from very close in, and the coupling is about 0.1. Back off to the size of a proton, and the coupling climbs toward 1. So the statement, the strong coupling equals 0.1, is meaningless until you say at what energy. And once you say at what energy, you have introduced a scale. The running is logarithmic. The coupling changes slowly, by the same increment every time the energy changes by a factor of 10. That slowness is what makes the whole thing possible. Start at an enormous energy where the coupling is tiny and slide down. The coupling grows, slowly, patiently, through 100 factors of 10, and then it reaches 1, and everything nonlinear happens at once. The energy at which it does that is called lambda, and for the strong force it is about 200 million electron volts. That is the trick. You began with a pure number and no scale, and you ended with a specific energy, because the pure number specified how far you had to slide before the force became strong. The proton's mass is not written into the theory. It is where the sliding stops. The consequences of this are worth holding still for. The strong force did not need a Higgs field to make mass. It did not need any input parameter with units. It generated a mass scale out of a dimensionless number and a logarithm. And because the running is logarithmic, an ordinary coupling at a high energy produces a very low lambda. Change the coupling at the high scale by a modest amount, and lambda moves by a factor of 1,000. Small changes upstairs, enormous changes downstairs. Nature can produce a proton weighing 1/1000th of the Planck mass without anyone tuning anything to 9 decimal places. Sidney Coleman and Eric Weinberg worked out the general phenomenon in 1973 in a paper about how a theory with no mass scale can spontaneously make one. It applies far beyond the strong force. It applies to any force that gets stronger as it goes out. So put the pieces together. You have a mechanism that takes a dimensionless number and converts it into a mass. You have a force that hides its constituents so completely that no one has ever seen one alone. You have bound states whose weight is nearly all field energy. And you have 5.4 times as much dark matter as ordinary matter, made of something with a mass nobody can explain, that nobody has ever seen alone, and that does not interact with anything we know. Ask the obvious question. Not whether dark matter is made of quarks, because it is not. Ask whether the universe used this trick twice. Nothing in the mathematics of Yang and Mills says there should be exactly one strong force with exactly 3 colours. The structure is a template. You pick a symmetry group, you pick how many kinds of matter carry the charge, and the theory writes itself. Nature chose 3 colours and 6 flavours for the force we know, and the choice looks arbitrary, and no one has ever explained it. So consider a second copy, a new gauge group, call it SU with n colours, with n being 2, 3, 4 or more. A new set of force carriers, dark gluons, coupling to a new charge, dark colour, a new set of matter fields, dark quarks, carrying that charge, and one crucial stipulation. These fields carry no electric charge, no ordinary colour, no weak charge. They are blind to everything in the Standard Model, and everything in the Standard Model is blind to them. Physicists call this a dark sector, and when the new force confines, they call it dark quantum chromodynamics, or dark QCD. Now, let the machinery run. The dark coupling is a dimensionless number, so it slides logarithmically, and somewhere it reaches strength 1, and that energy is a dark lambda. Below that energy, the dark quarks are confined. They cannot travel alone. They bind into dark hadrons, and the mass of each dark hadron is set almost entirely by the dark lambda, not by whatever masses the dark quarks were given. Dark mass from dark binding energy, exactly as before. Nothing about this is exotic mathematics. It is the same equation with different labels. What it buys you is precisely the thing the WIMP could not offer. The dark matter's mass is no longer a number you choose. It is the output of a running coupling generated from within, insensitive to the details, naturally far below whatever high energy the theory started at. And the dark lambda need not equal ours. It is set by where the dark coupling begins its slide, and how many dark quarks and colours there are. It could be 1,000th of ours so that dark protons weigh less than an electron. It could be 1,000,000 times ours, so that a dark hadron weighs as much as a bacterium's worth of protons. The freedom is real, but it is a freedom of one number, not of a dozen. Look at what such a sector automatically provides. It provides stability, because dark hadrons, like our protons, can be protected from decay by a conserved quantity, the dark equivalent of baryon number, which nothing violates. It provides a particle with mass and no electric charge. It provides self-interaction, since dark hadrons scatter off each other through dark nuclear forces the way our neutrons do. And it provides a rich spectrum because a confining force never makes one particle. It makes families. Here is where the ordinary picture of dark matter begins to look impoverished. Almost every calculation in the field treats dark matter as a single species of structureless particle. But if you were made of dark matter and looked at us from the outside and you asked what visible matter is made of, the honest answer would not be one particle. It would be quarks and gluons and hundreds of composite states, and nuclei and atoms and chemistry. Ordinary matter is not simple. There is no principle that says the majority of the universe's matter has to be simpler than the minority, which raises the practical objection, the one that has to be answered before any of this counts as physics. If this sector is truly blind to us, and we to it, how did it get here? How did its abundance get set? And how could we ever know? Two theorists asked those questions in 2006 and gave the whole picture a name. Matthew Strassler and Catherine Zurek published a paper in 2006 with a plain title about echoes of a hidden valley. It was 8 pages long, and it changed what a generation of experimentalists went looking for. The setup is easy to picture, and the picture is theirs. Imagine our world sitting on a plane with all its known particles, and imagine another world sitting in a valley beyond a ridge. The valley has its own particles and its own forces. Between the plane and the valley there is a barrier, a ridge that is high but not infinite. At everyday energies nothing crosses. The valley is invisible not because it is infinitely far away, but because we have never had enough energy to get over the ridge. The barrier, concretely, is a heavy particle, something that carries both ordinary charge and dark charge, and therefore talks to both sectors, but weighs enough that producing it takes a great deal of energy. Call it a mediator. Below the mediator's mass, the two sectors barely notice each other, and every interaction between them is suppressed by the mediator's weight. That suppression can be enormous. Above it, the barrier disappears and things cross freely. This structure does a lot of work at once. It explains why the dark sector was in thermal contact with ordinary matter in the very early universe, when everything was hot enough to make the mediator freely, so both sectors shared a temperature and a common history. It explains why they decoupled as the universe cooled, and the mediator became too heavy to produce, and it explains why we have never seen the dark sector since. Strassler and Zurek's real contribution was to say what a hidden valley looks like at a collider, because that is where a barrier of this kind might actually be crossed. Collide 2 protons at the Large Hadron Collider with enough energy to make the mediator. It decays, and it can decay into the valley, producing dark quarks. Those dark quarks are subject to a confining force, so they do exactly what our quarks do. They fly apart, stretch a dark colour string, snap it, and produce a shower of dark hadrons. dozens of them moving together, a dark jet. Now the question is, what happens to those dark hadrons? Some may be stable, and they simply leave the detector without a trace, showing up as missing energy. Others may be unstable, and here is the subtlety: they can only decay back through the mediator, back over the ridge, into ordinary particles. That decay is suppressed by the mediator's mass, which means it is slow, which means the dark hadron travels a measurable distance before it dies. Millimeters, centimeters, meters. The detectors at the Large Hadron Collider were designed for particles that either come from the collision point or do not exist. A particle that appears out of nothing, 30 centimeters from the beam pipe, in the middle of the tracking chamber, was the kind of event that trigger software was written to discard as noise. Strassler and Zurek pointed out politely that the experiments might have been throwing away the discovery for years. The name Hidden Valley became an organizing idea. It gave a common frame to a scattered collection of models, including dark QCD, and it turned an abstract worry into a set of searches with names like displaced vertices, emerging jets, and semi-visible jets. Those searches are running now. But before asking what a dark sector does at a collider, you have to ask what it is made of. In our world, the lightest particle a confining force produces is not the proton. It is something much lighter, and its lightness is not an accident. The pion weighs 135 million electron volts. The proton weighs 938. Both are made of the same quarks, held by the same force, confined in a region of the same size. The proton's mass came out of the box, out of the confinement scale, out of lambda. So why is the pion 7 times lighter? Because the pion is not really a bound state doing what bound states do. It is a ripple in the vacuum. Set the up and down quark masses to 0, which is nearly true, since they weigh only a few million electron volts in a theory whose natural scale is 200. In that idealized world, the theory has a symmetry. You can rotate left-handed quarks and right-handed quarks independently, and nothing changes. Left-handed and right-handed refer to whether a particle's spin points along its direction of motion or against it, and for a massless particle that distinction is absolute, because you can never overtake it and see the motion reverse. The strong force does not respect that symmetry, not in the vacuum. The vacuum of quantum chromodynamics is not empty. It is filled with a condensate, a sea of quark-antiquark pairs, each pairing a left-handed quark with a right-handed antiquark. Yoichiro Nambu understood this in 1960, working by analogy with superconductivity, where a similar condensate of electron pairs fills the metal. The condensate has picked out an alignment between left and right. The symmetry still exists in the equations, but the vacuum does not share it. Physicists say the symmetry is spontaneously broken, meaning the laws have it and the world does not. Jeffrey Goldstone proved a theorem about what happens next. Whenever a continuous symmetry is spontaneously broken like this, the theory must contain a massless particle for every direction in which the symmetry was broken. The reason is intuitive. If the vacuum picked one alignment out of a continuous family of equally good alignments, then slowly rotating the alignment from place to place costs nothing in the limit of infinite wavelength. A very long, very slow wave in the direction of the broken symmetry has almost no energy. A particle whose energy goes to 0 as its wavelength goes to infinity is a massless particle. Those particles are called Nambu-Goldstone bosons. In the strong force there are 3 of them, and they are the 3 pions. Because the up and down quarks are not exactly massless, the symmetry was slightly imperfect to begin with, and the pions pick up a small mass. That is why the pion is light and not 0. Its mass squared is proportional to the quark mass, a relation worked out by Murray Gell-Mann, Robert Oakes, and Bruce Renner in 1968. Now apply the theorem to a dark sector. Any confining dark force with more than one flavour of light dark quark will form a condensate, break its own chiral symmetry, and produce dark pions. Those dark pions will be the lightest states in the entire dark spectrum, lighter than the dark protons, lighter than everything. Whatever else the dark sector contains, the dark pions are what a cooling universe would be left holding. They come with a difficulty, and it is worth naming before it is solved. Pions are not stable. Ours decay, and a dark matter candidate that decays before the present day is not dark matter at all. But that instability depends on what the dark pion can decay into, in a sector cut off from ours by a heavy mediator, and with a symmetry that forbids the decay, the dark pion can live forever. Then a second difficulty arrives, sharper than the first. If the dark pions do not talk to us, they cannot annihilate into our particles, and freeze out as everyone learned it does not happen. There would be far too many of them, and the universe would have collapsed. Solving that problem required letting 3 particles become 2. Freeze out, as the Wimp Hunters used it, requires a door between the 2 worlds. 2 dark matter particles meet, annihilate, and turn into ordinary particles, photons or quarks or electrons, which carry the energy away. The universe expands, the dark particles get too dilute to find one another, and the annihilation shuts off. What remains is the relic abundance. The whole calculation depends on the dark particle being able to convert itself into our stuff. Take that door away, as a genuinely hidden sector does, and the calculation collapses. Dark pions have nothing to annihilate into. They cannot become photons because they do not couple to photons. They would simply persist, all of them, in the enormous numbers a hot early universe produces, and their combined mass would have shut the expansion down long before the first galaxy. The universe we live in would not exist. In 2014, Jonit Hochberg, Eric Kuflick, Toma Valansky, and Jay Wacker pointed out that there is another way for a population of particles to thin itself. It does not need a door. 3 dark pions meet, and 2 come out. The mass of the third becomes kinetic energy shared by the survivors. Nothing leaves the dark sector. The number of particles drops by a third with every such event, and the freeze-out proceeds on the strength of the dark sector's own interactions with itself. They called these particles strongly interacting massive particles, and the acronym deliberately is SIMP. The reaction has to actually be allowed, and this is the part that turns a clever idea into a piece of real physics. 3 particles into 2 is an odd process. It changes the number of pions by 1, and in a naive theory of pions, the number of pions modulo 2 is conserved, so it is forbidden. But our own strong force violates that rule, and it does so through something called the Wess-Zumino-Witten term, a piece of the pion theory that carries the memory of the quarks and gluons underneath. It is the same term that lets a neutral pion decay into 2 photons, which it does in about 8 times 10 to the minus 17 seconds, one of the best measured processes in physics. Julian Wess, Bruno Zumino, and later Edward Witten showed that the term must be there, and that its size is fixed entirely by the number of colours. So the 5-pion interaction is not optional. Any confining theory with enough flavours of light quark has it, and its strength is set by the number of dark colours and by the confinement scale. Run the freeze-out with that interaction and a number falls out. For the process to shut off at the right moment and leave 27% of the universe, the dark pion should weigh something like 100 million electron volts, and the dark confinement scale should be a few times that. Not the weak scale, not the mass of 100 protons, roughly the mass of our own pion. There is a catch, and Hochberg and her colleagues were direct about it. When 3 become 2, the survivors take the leftover mass as speed. The dark matter heats itself up as it thins. If nothing carries that heat away, the dark matter stays warm, streams out of small structures, and erases the dwarf galaxies we observe. So the dark sector needs some tiny leak to ours, enough to dump heat into the ordinary plasma, far too small to see in a detector. The door is not absent, it is nearly shut. What the SIMP picture gives you then is a dark matter whose mass comes from confinement, whose abundance comes from its own internal dynamics, and whose defining property is that it interacts with itself strongly. That last feature is not a nuisance. For 15 years before anyone wrote the SIMP paper, a small group of astrophysicists had been arguing that dark matter behaves as though it does exactly that. Cold dark matter, simulated on a computer, builds halos with a particular shape. Julio Navarro, Carlos Frenk and Simon White described it in the mid-1990s, and the profile carries their initials. The density climbs steadily toward the centre and keeps climbing steeper and steeper in a spike astronomers call a cusp. Every simulation of collisionless dark matter produces one. The particles fall in, pass through and never scatter, so nothing prevents the pile from sharpening. Look at real dwarf galaxies, which are the cleanest place to check because they are almost entirely dark matter, with a little gas and a few stars, and the spike is not obviously there. Rotation curves in many of them suggest a flat central region instead, a core with roughly constant density across the innermost few hundred light-years. This is the core cusp problem, and it has been argued about since the 1990s. Two other tensions arrived alongside it. Simulations predicted that a galaxy like the Milky Way should be surrounded by hundreds of satellite dwarf galaxies, and for years only a dozen or so were known. And the most massive predicted satellites should have been bright enough to see, yet the brightest observed satellites appeared to sit in shallower gravitational wells than the simulations demanded. The second issue got the memorable name, too big to fail. In 2000, David Spergel and Paul Steinhardt proposed a single change. Let dark matter scatter off itself, not off us, off itself, elastically, like billiard balls, with a cross-section per unit mass somewhere between roughly 0.1 and 10 square centimeters per gram. That number wants a picture. Take a dark matter particle sitting in the halo of a dwarf galaxy. It orbits for 10 billion years. With a cross-section per mass of about 1 square centimeter per gram, it will scatter off another dark matter particle roughly once in that entire time, near the dense centre, and essentially never in the sparse outskirts. It is the gentlest possible collisionality, and it is enough. A few scatters in the core let fast particles from the outside carry energy inward, and slow particles from the inside drift outward, and the cusp relaxes into a core over the age of the universe. Notice how naturally this falls out of a confining dark sector. Our own neutrons scatter off each other with a cross-section set by the size of a nucleon, which is set by lambda. Do the same arithmetic with a dark hadron whose mass is a few 100 million electron volts, and you land in the range Spergel and Steinhardt wanted, without arranging anything. A composite particle made by a strong force is self-interacting, because that is what composite particles made by strong forces do. The WIMP had to be given self-interaction by hand, and nobody had a reason to. The honest state of the argument is that the astrophysical case has weakened, and it has weakened for a good reason. Simulations that include ordinary matter now do better. Supernovae exploding near the centre of a dwarf galaxy blow gas outward. The gravity of that gas tugs the dark matter with it, and repeated cycles of outflow can flatten a cusp into a core without any new physics. Deeper surveys have found dozens more Milky Way satellites, and the missing satellite count has largely been reconciled. Feedback is messy and hard to model, and different groups reach different conclusions. So the small-scale puzzles are a hint, not a proof. What they are not is arbitrary. They point at a specific number, a cross-section per mass of order 1 square centimeter per gram, and that number can be tested somewhere feedback cannot reach. Return to the bullet cluster, the two clusters that pass through each other while their hot gas piled up in the middle. It is the cleanest experiment on dark matter's self-interaction that anyone will ever be handed, because nobody had to build it. Consider what the collision was. Each cluster carried a halo of dark matter weighing something like 100 trillion suns. Those halos drove through each other at about 4,000 kilometers per second. If the dark matter scattered off itself readily, 3 things would happen. The 2 halos would slow, lagging behind the galaxies they were supposed to be carrying. They would lose mass, as scattered particles were stripped out and left near the collision axis. and the trailing halos would be pulled back toward the middle, so the lensing peaks would sit closer to the X-ray gas than to the galaxies. None of that is seen. The lensing maps put the mass on top of the galaxies, out ahead, and Douglas Close's measurement bounds how much could have been left behind. Marusa Bradak, Maxim Markovich, Scott Randall and others turned the picture into a number. The dark matter self-interaction cross-section per unit mass is less than about 1 square centimetre per gram, and depending on which effect you use and how conservatively you treat the systematics, the bound tightens towards 0.5. Put that in human terms. 1 square centimetre per gram is close to the cross-section per mass of a proton scattering off a proton through the strong force. A dark matter particle would have to be roughly as sticky, pound for pound, as ordinary nuclear matter, and no more. Other bounds come from the shapes of halos. A self-interacting halo relaxes toward a sphere, since scattering isotropizes the orbits. Real cluster halos, mapped by lensing, are somewhat elongated. Cluster cores, measured across dozens of systems, are not as large as strong self-interaction would carve, and the offsets between mass and galaxies claimed in a few individual systems have mostly failed to survive better data. A widely reported offset in the cluster Able 3827 was retracted when deeper Hubble imaging arrived, so the cluster bound and the dwarf galaxy preference pull against each other. Dwarfs want roughly 1 square centimetre per gram or more. Clusters allow less than 1 and prefer well under it. Taken as constant numbers, they do not comfortably coexist. Here is the escape, and it is not an excuse invented for the occasion. Real nuclear scattering is not constant with velocity. It rises and falls, it has resonances, it depends strongly on how fast the nuclei approach. Neutron scattering cross-sections vary by orders of magnitude across a modest range of energies. Any self-interaction mediated by a force with a range, rather than by contact, falls off as the collision gets faster, because a quick pass leaves less time for the force to act. Dark matter in a dwarf galaxy moves at about 30 kilometers per second. In a galaxy cluster, it moves at 1,000 or more. That is a factor of 30 in speed, and a mediated interaction can easily change by a factor of 100 across it. A cross-section that is large and helpful in the dwarfs and small and invisible in the clusters is not a fudge. It is the default behavior of a composite particle interacting through an exchange mediator, which is precisely what a dark hadron is, which makes velocity dependence the sharpest thing to look for and turns a vague hint into a falsifiable prediction. Now consider a dark sector arranged to hide in a different way, one where the constituents are not hidden at all. Nothing forces a dark sector to be entirely blind to us. It could be that the dark quarks carry ordinary charge, feel the electromagnetic and weak forces, and are perfectly ordinary in that respect, while the bound states they form are neutral, and neutral in an unusually thorough way. Start with the neutron. It is made of 3 quarks with electric charges of 2/3, -1/3, and -1/3, adding to 0. A neutron is electrically neutral. It is not electromagnetically inert. It has a magnetic moment because the charged quarks inside are spinning and moving. Put a neutron in a magnetic field and it responds. So neutron-like dark matter would have been found in a xenon detector years ago. Now make a dark baryon with spin 0. Its constituents carry electric charge. It has no charge and no spin, therefore no magnetic moment, and no charge radius either, because charge radius requires a non-zero charge distribution that the quantum numbers forbid. What remains is polarizability. Sit the particle in an electric field, and the charge constituents inside shift slightly, giving it an induced dipole. That is the leading interaction it can have with a photon, and it is suppressed by the 4th power of the particle's mass. Make the particle heavy, around 1 trillion electron volts, and the suppression is savage. Physicists at Lawrence Livermore, Yale, Colorado, Oregon, and Argonne, working as the Lattice Strong Dynamics collaboration, gave this idea a name: stealth dark matter. Among them were Thomas Appelquist, Graham Cribbs, Ethan Neal, and Enrico Rinaldi. The theory is a confining force with 4 colours rather than 3, containing dark quarks that carry electroweak charge and pair up into a spin-zero, electrically neutral stable baryon. What makes this work worth telling is not the model, it is the method. To know whether such a particle is already excluded, you need its polarizability, which is a property of a strongly coupled bound state, which nobody can calculate with pencil and paper. So they did what Zoltan Fodor's group did for the proton. They put the theory on a lattice, generated field configurations, and measured the mass spectrum and the electromagnetic form factors of a particle that has never been observed and may not exist. Take that in. A supercomputer computing, from first principles, the response to an electric field of a hypothetical composite object made of hypothetical constituents bound by a hypothetical force. The result told them how deep a xenon experiment must go to see it, and the answer was that a stealth baryon heavier than about 300 billion electron volts hides below the reach of current detectors, and in some of the parameter space, below the neutrino fog. The constituents, though, are not hidden. They carry electroweak charge, so the Large Hadron Collider can make them directly. They would be produced, they would confine, and they would leave signatures. Nothing has been seen, which pushes their masses up, which is a real and ongoing constraint. The particle hides. The pieces it is made of do not. Stealth dark matter is not the most popular version of a dark strong force, and it may well be wrong. It earns its place here because it shows what a composite dark matter candidate does that an elementary one cannot. It has structure. Structure produces form factors, and form factors suppress interactions in ways that no elementary particle can arrange without fine-tuning. A dark matter that is hard to see because it is made of something is a different kind of dark matter than one that is hard to see because it was declared weakly coupled. And there is one more thing composite dark matter can explain, which no elementary candidate has ever explained at all: the number 5. Recall the coincidence. Dark matter outweighs ordinary matter by a factor of 5.4. Ordinary matter's abundance was set by a tiny surplus of matter over antimatter, 1 part in a billion, frozen in after everything else annihilated. Dark matter's abundance in the freeze-out picture was set by an annihilation rate. 2 unrelated mechanisms and a suspiciously modest gap between the results. Suppose instead that the same surplus set both. Imagine an early process, at high energy, that produces a small imbalance and shares it between the 2 sectors. Whatever generated 1 extra proton per billion also generated a matching number of extra dark baryons per billion. The dark antibaryons then annihilate against the dark baryons thoroughly until only the surplus is left, exactly as happened here. The universe ends up with a number of dark baryons comparable to the number of protons, not by coincidence, but because they were counted out together. If the numbers are comparable, then the mass ratio tells you the mass. 5.4 times as much dark matter, with a comparable number of particles, means each dark particle weighs about 5 times a proton, a few billion electron volts, not 100 times the proton where the WIMP lived. 5 times. Shmuel Nusinov saw the shape of this argument in 1985 when he suggested that dark matter might be a technibaryon, a bound state of a new strong force, carrying a conserved charge shared with ordinary baryon number. The idea was developed and named by David Kaplan, Marcus Luty, and Catherine Zurek in 2009. They called it asymmetric dark matter. The sharing mechanism has to be real physics, and there is one available. The standard model, at temperatures above roughly 100 billion electron volts, contains processes called sphalerons, which violate baryon number and lepton number while preserving their difference. They are not exotic add-ons. They follow from the weak force and the structure of its vacuum, and every model of how the matter surplus arose relies on them. If the dark sector carries a charge that the sphalerons also touch, or if some heavy particle decays into both sectors and carries a shared charge, the 2 surpluses come out linked, with the ratio set by the group theory of who couples to what. Now look at what this does when you combine it with a dark, strong force. The dark baryon is stable, protected by its own conserved baryon number. The same reason our proton does not decay. Its mass is set by dark confinement, by a dark lambda that the running coupling produces from nothing. And the asymmetric argument tells you where that lambda should sit. Around 1 billion electron volts, within a factor of a few of our own. Two entirely different arguments, one from cosmology and one from the structure of the theory, converge on a dark confinement scale close to the ordinary one. That convergence has the same flavour as the WIMP miracle, and it deserves the same suspicion. Sharing the asymmetry requires a mechanism. The mechanisms are not unique, and the ratio between the two surpluses depends on details nobody has measured. A factor of 5 can be arranged. It can also be missed by a factor of 10. What it does by is a target. Dark matter of a few billion electron volts is light by WIMP standards, and it deposits very little energy when it strikes a xenon nucleus. It sits precisely in the region where liquid xenon detectors run out of sensitivity, and where a newer generation of experiments using silicon, helium, and superconductors is now being built. For 30 years the searches looked heavy. The strong force suggests looking light. Before leaving the spectrum, there is one kind of particle a confining force makes that has no analogue among anything you have ever touched. Take a confining force and remove all its matter. No quarks, no dark quarks, nothing carrying the charge except the force carriers themselves. In ordinary electromagnetism, this would leave you with an empty theory, since photons ignore photons and light in a vacuum does nothing at all. In a Yang-Mills theory, it leaves you with something else. The gluons carry colour, so they pull on one another, and a theory of nothing but gluons still confines, still has a scale, and still has particles. Those particles are glueballs. They are bound states of force. There is nothing inside them but field. Our own strong force should have them, and they should be there in the debris of ordinary collisions. Lattice calculations, refined over decades by Michael Tieper, Colin Morningstar, Mike Pearden and others, put the lightest glueball, the one with zero spin and even parity, at about 6.8 times lambda, which comes to roughly 1,700 million electron volts. Experiments have found several particles in that region with roughly the right properties, and nobody can say with confidence which one is the glueball, because a glueball with the right quantum numbers will mix freely with ordinary mesons made of quarks. The clean prediction is muddied by the very quarks that make the world visible. In a dark sector with no light dark quarks, nothing muddies it. The glueballs are the entire spectrum, and the lightest one is a legitimate dark matter candidate. Alon Faraghi and Maxim Pospelov proposed this in 2000, and Kimberly Boddy, Jonathan Feng, Manoy Kaplinghat and Tim Tate worked out the cosmology carefully more than a decade later. The particle is neutral because there is nothing in it to carry charge. It is stable because there is nothing lighter for it to become, provided its decays back to our sector are suppressed. It self-interacts, because glueballs scatter off glueballs through the same self-coupling that made them. Its abundance is set by a variant of the 3-into-2 process. Glueballs are their own antiparticles, so they cannot annihilate in pairs into nothing. But 3 glueballs can become 2, and the leftover mass becomes speed, and the population thins by its own internal dynamics until the reaction shuts off. Boddy and her colleagues found that this works, that it gives the right relic density, and that it prefers a glueball mass somewhere between about 100 million and 100 billion electron volts, depending on how hot the dark sector was compared to ours. Sit with what a glueball is for a moment longer, because it is the purest illustration of the chapter you read first. The proton's mass is almost all field energy, but a purist could object that there are still 3 quarks in there, and quarks have mass, however little. A glueball has no such excuse. Every last electron volt of its mass is the energy of a self-tangled field. It weighs something for the same reason a knot in a rope has length. Nothing is inside it. The knot is the thing. If the dark sector is made of glueballs, then dark matter is not a substance in any sense a chemist would recognize. It is tension. It is the strong force alone, folded up. That version is elegant, and it is nearly untestable, which is a fair criticism. A glueball dark sector has no charged constituents, no easy portal, and no obvious signature at a collider. It sits at one extreme of the possibilities. At the other extreme is a dark sector with several light quarks, several stable hadrons, and a long-range force between them, and that sector would not stay simple for long. Ordinary matter did not stop at protons. Protons and neutrons found each other and stuck, held by the residue of the strong force, leaking out past the edge of each hadron, and in the first few minutes of the universe that residue built helium, deuterium, and a trace of lithium. Then electrons arrived, bound electrically, and matter acquired chemistry. Every complicated thing in the universe followed from the fact that the strong force does not quite stop at the surface of a proton. There is no reason a dark strong force would stop at the surface of a dark hadron either. Gil Paz, Gordon Krnjajic, Chris Sigurdsson and others have taken the idea seriously. Dark nucleosynthesis. If the dark sector has more than one stable baryon, and a residual force between them, it should build dark nuclei in its own first minutes. William Detmold, Matthew McCullough, and Andrew Paczynski went further and simulated a two-colour dark theory on a lattice to compute whether its baryons bind at all and how tightly. In ordinary nuclear physics, the binding energy of a nucleus is about 1% of its mass. A dark sector could easily bind 10 times harder or 10 times softer, and the difference would show up in how much energy is released when dark nuclei form, and in whether the dark matter today is monolithic or built into a spectrum of dark isotopes. Then there is the other force. Suppose the dark sector contains a massless dark photon, an unbroken copy of electromagnetism with no connection to ours. Dark protons and dark electrons would bind into dark atoms. David Kaplan, Gordon Krnjajic, Keith Reherman, and Christopher Wells worked out this scenario in 2009 and called it atomic dark matter. The dark hydrogen has a dark Bohr radius, dark spectral lines, and a dark recombination epoch. And here is the consequence that matters, the one that separates a dark sector with long-range forces from every other version. Atoms radiate. A cloud of atomic gas that falls into a gravitational well can collide, excite, emit photons, and lose energy. That is why ordinary matter cools, sinks to the centre of every dark matter halo, and flattens into a disk. It is why the Milky Way is a disk of stars inside a sphere of dark matter. Ordinary matter dissipates. Standard dark matter cannot, so it stays puffed out and round. Give dark matter a dark photon and it can cool too. Lisa Randall, Gigi Fan, Andre Katz, and Matthew Rees proposed that a small fraction of the dark matter, a few percent, might be dissipative and might have collapsed into a thin dark disk lying inside the plane of our own galaxy. We would be sitting in it, orbiting through it, and it would show up as a subtle extra pull on stars moving perpendicular to the galactic plane. Gaia, the European satellite that has mapped the motions of nearly 2 billion stars, is precise enough to look for exactly that. So far, the data constrain such a disk severely and do not require one. The bulk of the dark matter cannot be dissipative. If it were, every halo would have collapsed into a disk, and the bullet cluster mass would have behaved like the gas rather than like the galaxies. Halo shapes forbid it, and the shapes are measured. But a subcomponent is allowed. The universe permits a hidden sector with its own nuclei, its own atoms and its own thin structures, provided it is a minority. Nobody knows whether it is there. What is worth holding on to is the shape of the question. If a dark, strong force exists, the interesting object is not one particle. It is a periodic table. Everything so far has treated the dark sector as sealed. If it truly were, this would be theology rather than physics, since a world that cannot touch ours cannot be tested by us. The two sectors must communicate somehow, at some level, or they would never have shared a temperature in the early universe. There are only a few ways to build a bridge, and they are constrained by symmetry. Physicists call them portals, and the list is short because the standard model contains only 3 quantities that can pair with a neutral dark field without breaking any rule. The first is the photon's own field strength. In 1986, Bob Holdham pointed out that if the dark sector contains its own copy of electromagnetism, its dark photon can mix quantum mechanically with ours. A dark photon is not exactly a dark photon. It is a superposition, faintly tinged with the ordinary photon, and the size of the tinge is a single number physicists call epsilon. The mixing can arise from any heavy particle that carries both charges running in a quantum loop. The effect is that ordinary charge particles acquire a tiny dark charge, proportional to epsilon, and dark particles acquire a tiny electric charge. Epsilon is typically expected to be somewhere between 10 to the -6 and 10 to the -3, which is small enough to hide and large enough to matter. The second is the Higgs field. The Higgs is the only fundamental scalar in the standard model, and a scalar can pair with any other scalar without offending any symmetry. So a dark scalar can mix with the Higgs, and the Higgs boson can decay, invisibly, into dark particles. The Large Hadron Collider measures the Higgs decay rates, and about 10% of Higgs decays could still be invisible without contradicting the data. That 10% is a large window. The third is the neutrino. A heavy neutral fermion can pair with the standard model neutrinos, and that bridge connects the dark sector to the least understood particles we have. Add to these the heavy mediator of the hidden valley, a particle carrying both dark colour and ordinary colour, weighing perhaps a few thousand billion electron volts, too heavy to make except at the highest energies. The point of a portal is that it is small but not zero. That single property carries the entire experimental program. It is why the dark sector was in thermal contact when the universe was hot, and it froze out when the universe cooled. It is why dark hadrons can decay back to ordinary particles slowly rather than never, so a collider can see them appear late. It is why a direct detection experiment has any hope at all, since a dark hadron scattering off a xenon nucleus does it by exchanging a dark photon that is faintly electric. It is why fixed target experiments like Na-64 at CERN and proposed detectors like the light-dark matter experiment fire beams into blocks of material and look for the momentum that walks away. And it is why supernova 1987A, the star that exploded in the Large Magellanic Cloud and briefly outshone a galaxy in neutrinos, still constrains this physics. A dark sector coupled too strongly would have carried energy out of the collapsing core, shortening the neutrino burst below the 10 seconds observed. 12 neutrinos, detected in Japan and Ohio in 1987, still rule out regions of parameter space 40 years later. The portal cuts both ways. It lets us look in. It also lets dark quarks be manufactured in a proton collision, where they will do what quarks do. 2 protons collide inside the Large Hadron Collider at a center of mass energy of 13,000 billion electron volts. Occasionally, if the theory is right, the collision makes a heavy mediator, a particle carrying both ordinary color and dark color. It lives for an instant and decays into a dark quark and a dark antiquark, flying apart at nearly the speed of light. Now the dark, strong force does its work. A dark color string stretches between them, and it snaps over and over, converting the energy of separation into dark hadrons. What emerges is a shower of dark pions and dark rho mesons and whatever else the spectrum contains, dozens of particles moving in a tight cone, a dark jet. The dark hadrons then face a choice made for them by the theory. Some are stable and simply leave, carrying momentum away invisibly. Others are unstable, and they can only decay through the portal, back across the ridge, into ordinary quarks. That decay is suppressed by the heavy mediator's mass to the 4th power, which makes the dark hadron long-lived. Give a dark pion a mass of a few billion electron volts, and a mediator at a few thousand billion, and its flight distance before decaying comes out in millimeters or centimeters, occasionally meters. Pedro Schwaller, Daniel Stolarski, and Andreas Weiler worked out the picture in 2015 and gave it a name, an emerging jet, merging. The dark hadrons stream out from the collision point invisibly, and then, spread along their flight path, they begin to decay. Ordinary charged tracks appear out of empty space, one after another, at 10 centimeters, at 15, at 30. There is no vertex at the beginning of the jet. The jet emerges from nothing gradually as it travels. Nothing in ordinary physics does that. A jet from an ordinary quark starts at the collision point with 100 tracks all pointing back to it. An emerging jet has no tracks near the beam and a growing number farther out. The background is not small, it is essentially absent, which is the best thing a search can have. There is a companion signature for the case where some dark hadrons stay stable. Then part of the jet's energy simply vanishes, and the detector records a jet whose momentum does not balance, with missing energy pointing along the jet axis rather than away from it. Timothy Cohen, Mariangela Lisanti, and Ho Kyung Lu called these semi-visible jets. Standard searches for missing energy actively veto events where the missing momentum lines up with a jet, because in ordinary physics that means a mismeasured jet. The search was designed to throw the signal away. That is the recurring lesson from Strassler and Zurek, restated in hardware. The CMS collaboration published a dedicated emerging jet search in 2019, and a stronger one since. An atlas has looked for displaced vertices and semi-visible jets. Nothing has been found. Mediator masses below roughly 1 to 2,000 billion electron volts are excluded for the simplest versions, and the searches continue as the collider accumulates data. What makes these searches worth their cost is not the probability of success. It is that they are looking for a phenomenon that follows necessarily from the premise. If there is a confining force in a dark sector, and if any portal connects it to us, then dark showers exist and dark hadrons have lifetimes. You do not get to have one and not the other. The signature is not a model builder's choice, it is a consequence. There is one more consequence of the strong force nobody chose, and it is the strangest fact in this entire subject. Our own strong force, the one in your hand, has a knob that is set to 0 for no reason at all. The equations of quantum chromodynamics permit one term that nobody wants. It is allowed by every symmetry the theory has. It is not forbidden by anything. It comes with a number in front of it, an angle, written as theta, which can take any value between 0 and 2 pi, and the theory says nothing about which. What the term does is violate a symmetry called CP, which relates a process to its mirror image, with particles swapped for antiparticles. If theta is not 0, the strong force distinguishes between a process and its mirrored charge-flipped version. The observable consequence is specific and beautiful. A neutron would become slightly lopsided. Its positive and negative charge, which sum to 0, would fail to sit at the same centre, leaving the neutron with a permanent electric dipole moment aligned with its spin. Nothing else in the neutron structure produces this. It is a direct reading of theta. So people measured it, and they have been measuring it for 70 years, starting with Norman Ramsey and James Smith and Edward Purcell in the 1950s. The technique is to take ultra-cold neutrons, so slow they can be stored in a bottle, apply electric and magnetic fields, and watch for a shift in how fast the neutron spin precesses when the electric field flips direction. The most sensitive result, published in 2020 by a collaboration at the Paul Scherrer Institute in Switzerland, found nothing, with an uncertainty around 1 part in 10 to the 26th of an electron times a centimetre. To picture that sensitivity, scale the neutron up to the size of the Earth. The measurement says its positive and negative charge centres are separated by less than the width of a few atoms. Translating that into theta gives a bound of about 10 to the minus 10. Theta could have been anything on a circle. It sits within a 10 billionth of 0. This is not a small anomaly. It is one of the largest unexplained numbers in physics, and the reason it is glaring is that the other forces are not shy about CP violation at all. James Cronin and Val Fitch discovered in 1964 that the weak force violates CP, and it does so with an angle of order 1. The weak sector has its knob turned nearly all the way up. The strong sector has an identical knob set to 0 to 10 decimal places, and no known reason for it. You can simply declare theta to be 0 as an initial condition. That works, in the sense that no calculation contradicts it. It is unsatisfying in the way that finding a pencil balanced on its point is unsatisfying. Nothing forbids it. It just does not happen unless something is holding the pencil. There is a second escape, and it is not chosen by nature. If any quark had exactly 0 mass, theta would become unobservable, absorbed into a redefinition of that quark's field. The up quark's mass is small, but lattice calculations have established that it is not 0, and the escape is closed. So the strong force presents an unexplained 0, at the same time that cosmology presents an unexplained mass. In 1977, 2 physicists at Stanford proposed a way to explain the 0. They were not thinking about dark matter. What they found made theta relax to 0 on its own, and it left behind a particle nobody asked for, which turns out to be one of the best dark matter candidates in existence, and whose mass comes directly from the strong force. Roberta Pache and Helen Quinn were trying to solve one problem. Theta is a constant in the theory, a number written into the equations, and constants do not relax to anything, so they proposed that theta should not be a constant. They introduced a new symmetry, a rotation of the quark fields that changes theta, and they arrange for the universe to spontaneously break that symmetry, which converts theta from a fixed parameter into a dynamical field, free to move. Then the field rolls, and the strong force itself provides the hill it rolls down. Quantum chromodynamics generates a potential energy for theta, and that potential has its minimum, provably, at theta equal to 0. Curtis Callan, Roger Daschen, and David Gross, and independently Claude Waffer and Edward Witten, established this. The vacuum settles at the bottom. Theta becomes 0 not because someone set it there, but because that is where the ball stops rolling. That is a satisfying solution to a hard problem, and it is not what made the idea famous. Pache and Quinn published in 1977. Within months, Steven Weinberg and Frank Wilczek independently noticed something the original authors had not spelled out. If you spontaneously break a continuous symmetry, Goldstone's theorem applies exactly as it did for the pion. There must be a new particle, a Nambu-Goldstone boson, corresponding to slow rotations of the broken symmetry. In this case, the particle is theta itself, oscillating about its minimum. Weinberg and Wilczek both realized this at nearly the same time, and Wilczek named the particle after a brand of laundry detergent because it cleaned up a problem, the Axion. The original version placed the symmetry breaking at the weak scale, which made the Axion weigh about 100,000 electron volts and couple strongly enough to be produced in kaon decays and beam dumps. Experiments went looking almost immediately, at CERN and Fermilab and elsewhere, and they killed it within a few years. The Axion in its first form was ruled out by 1978. The idea survived by moving. The scale at which the Pecky-Quinn symmetry breaks is a free parameter called f sub a, and nothing requires it to be the weak scale. Push it up to 10 to the 12th billion electron volts or beyond, and every coupling of the Axion to ordinary matter is suppressed by that same enormous number. Gene Kim, and separately Mikhail Schiffman, Arkady Weinstein, and Valentin Zakharov built one such model. Michael Dine, Willy Fischler, Mark Srednicki, and independently Anton Zhitnitsky built another. Their Axion couples to photons and electrons so feebly that it passes through the Earth, the Sun, and everything else, essentially untouched. They called it the invisible Axion. The name was a joke about experimental prospects, and it aged poorly in the best way. Notice what has happened here. A symmetry was invented to explain why a number is zero. It succeeded, and the price of success was a particle. That particle is neutral, extraordinarily light, and interacts with ordinary matter far more weakly than a neutrino. Nobody was trying to build a dark matter candidate. The theta problem produced one as a side effect, and refused to take it back. There are two things left to explain about it, and both connect straight back to the first chapter of this script, where the Axion's mass comes from, and why a particle that light is nonetheless cold. An Axion has no mass at all in the beginning. It is a Goldstone boson of an exact symmetry, and the theorem guarantees it is massless. But the Pecky-Quinn symmetry is not exact. Quantum chromodynamics breaks it through the same instanton effects that give theta a potential, and a slightly broken symmetry gives its Goldstone boson a small mass. This is precisely the pion story, told again. The pion is nearly massless because chiral symmetry is nearly exact, and its mass comes from the small quark masses that spoil the symmetry. The Axion is nearly massless because Pecky-Quinn symmetry is nearly exact, and its mass comes from the strong force that spoils it. The relation between them can be written down almost by hand. The Axion's mass times the Pecky-Quinn scale equals, up to a factor near 1, the pion's mass times the pion's decay constant. The pion contributes its own mass and its own scale, both of which are set by lambda, the confinement scale from chapter 13. So the Axion's mass is manufactured out of ordinary quantum chromodynamics, out of the same field that makes your hand heavy, divided by an enormous new number. Take the Pecky-Quinn scale to be 10 to the 12th billion electron volts, a common benchmark. The Axion's mass comes out around 6 millionths of an electron volt. That is roughly 100 billion times lighter than an electron. Its Compton wavelength, the natural size associated with such a mass, is a few tens of meters. Say plainly what this means. The Axion's mass is a shadow of the strong force in the most literal sense in this entire script. It is not made by a new confining force in a hidden sector. It is made by ours. The gluon field in the vacuum, condensing and tunneling between its degenerate configurations, gives the Axion its weight. Turn off the strong force, and the Axion becomes exactly massless. Now the second question. How can a particle weighing a millionth of an electron volt be cold dark matter, when the cosmic microwave background demands that dark matter was moving slowly when structure formed? A neutrino weighing far more than that is far too fast. The answer is that the Axion was never a gas of particles. In the early universe, the Axion field simply had some value, a random angle sitting somewhere on its circle, whatever the initial conditions handed it. That value was frozen, held still by the friction of cosmic expansion, because a field cannot roll faster than the universe lets it. Then, as the universe cooled and quantum chromodynamics turned on its potential, the Axion mass switched on, the friction became negligible, and the field began to oscillate about theta equals 0, like a pendulum released. A scalar field oscillating coherently about the minimum of its potential behaves exactly like a cloud of pressureless matter at rest. Its energy density dilutes as the universe expands, precisely as cold matter does. The Axions are not particles flying around. They are a single field, sloshing everywhere at once, with an enormous number of quanta occupying the same state, which is what physicists mean when they say the Axion is born cold no matter how light it is. John Preskill, Mark Wise, and Frank Wilczek worked this out in 1983. So did Larry Abbott and Pierre Zwicky, and separately Michael Dine and Willy Fischler. 3 papers, same journal, same issue. They found that if the Pecky-Quinn scale sits around 10 to the 12th billion electron volts, the misalignment mechanism produces the observed dark matter density. Not approximately. Right on it. Nobody arranged that either, and an Axion, unlike a wimp, can be heard. Pierre Zicky's insight, published in 1983, was that an Axion in a magnetic field is not quite invisible. The Axion couples to 2 photons weakly. Supply one of them by hand, as a strong static magnetic field, and the axion can convert into the other, a single real photon carrying the axion's total energy. That energy is mostly rest mass, since the axions in our galactic halo move slowly at around 230 kilometers per second. So an axion weighing a few millionths of an electron volt converts into a photon of a few gigahertz, a microwave, a radio signal. The device Zwicky proposed is a heloscope. Take a copper cavity, sized so that microwaves of a chosen frequency resonate inside it. Put it in the strongest magnetic field you can build. Cool it to near absolute zero so that thermal noise does not drown the signal. The dark matter halo passes through the cavity constantly, roughly 1 billion axions per cubic centimeter if the axion is microscopic enough, and if the cavity's resonant frequency happens to match the axion's mass, power builds up inside it. The power is around 10 to the minus 23 watts. To hear it, you must listen for minutes and then, because you do not know the axion's mass, move a tuning rod, shift the cavity's frequency by a fraction of a percent, and listen again. That is the experiment. It is a radio search across a band with no station guaranteed to exist, over a range of frequencies spanning several factors of 10, moved a fraction of a percent at a time. The Axion dark matter experiment at the University of Washington has been doing it since the 1990s, with an 8 Tesla magnet and amplifiers so quiet they operate near the limit that quantum mechanics permits. It has excluded the most theoretically motivated Axion models across a slice of frequency between roughly 600 MHz and 1.5 GHz. The slice is narrow, the band is wide, others are pushing at different frequencies with different geometries. Haystack at Yale uses squeezed quantum states to beat the standard noise limit. Organ in Australia works at higher frequency. Mad Max in Germany plans a stack of dielectric plates rather than a cavity. And DM radio hunts at frequencies so low that the apparatus is not a cavity, but a very large loop of wire. CAP in Korea runs several cavities at once. A different strategy entirely, the helioscope, points a magnet at the sun to catch axions produced in its core, which CAST at CERN has done for years, and which the proposed International Axion Observatory would do far better. None of them has found anything. That is the honest state of the field, and it is worth saying without flinching. What makes the search worth a lifetime is that the target is not a wish. If Pesci Quinn is right, the axion exists, its mass lies in a range that theory brackets, and its coupling to photons is fixed to within a factor of a few by the same quantum chromodynamics that fixes the pions' decay constant. The line the experiments are chasing is drawn on the plot before the data arrive, and the axion answers 3 questions at once, which nothing else does. It explains why the neutron is not lopsided, it supplies cold dark matter with the right abundance, and it takes its mass from the strong force, which means that if you found it, you would have found a piece of the universe whose weight was made by the same field that makes yours. Whether any of this can be true at all, though, depends on rules that cosmology sets, and that no clever model can talk its way around. A hidden sector is not free. It has to have existed alongside ours through the entire history of the universe, and cosmology has recorded that history in 2 independent ledgers. Both of them count energy. The first is nucleosynthesis. In the first few minutes, protons and neutrons fused into helium and deuterium, and how much of each depends sharply on how fast the universe was expanding at the time, which depends on the total energy density, which depends on how many kinds of light particle were present. Add extra light particles and the universe expands faster. Neutrons have less time to decay before they are captured, and more helium comes out. The observed helium abundance, about 24% by mass, is measured well enough to notice. The second is the cosmic microwave background. The same counting shows up in how the acoustic peaks are damped at small angular scales. Physicists fold it into a single number called the effective number of neutrino species, written n sub f. The standard model predicts 3.044, a value slightly above 3 because of subtleties in how neutrinos decoupled. Planck measures something consistent with it, with an uncertainty of about 0.17. Any dark sector particle that is light and relativistic at that time adds to n sub f. A single extra light species, thermalized with the same temperature as our photons, would add about 1, which is 6 standard deviations away from the measurement. So a dark sector cannot be both light and hot. It must be heavy, so that it has already turned non-relativistic, or it must be cold, meaning its temperature is lower than ours. That second option is not a dodge. If the two sectors decoupled early, before the ordinary plasma dumped the entropy of annihilating heavy particles into its photons, our side got hotter and theirs did not. A dark sector that decoupled at a few 100 billion electron volts naturally sits at about half our temperature, which suppresses its contribution to n sub f by the fourth power. Dark radiation is allowed. It is just quiet. There is a second class of constraint on how dark matter moved. A particle that streams freely at high speed wipes out density fluctuations smaller than the distance it travelled. Warm dark matter would leave the universe with no small galaxies. Astronomers test this using the Lyman alpha forest, the picket fence of absorption lines that intergalactic hydrogen clouds imprint on the light of distant quasars. Each line is a clump of gas. Counting the small clumps sets a floor on how cold dark matter must have been, and it is a demanding floor. A confining dark sector has a further hazard. Before it confines, its light particles behave like radiation. Dark photons, if present and massless, remain radiation forever. And if the dark matter is coupled to that dark radiation the way ordinary matter was coupled to light, then dark acoustic oscillations occur, and dark matter clumps get damped, and the small-scale universe changes shape. That effect is real, it is calculable, and comparing it with the galaxy counts constrains the dark coupling, so the universe imposes a set of rules on any hidden strong force. It cannot contribute too much radiation, it cannot be warm, it cannot have too much long-range dark electromagnetism, or halos would be disks. It cannot self-interact more than about 1 square centimetre per gram at cluster speeds. It must produce the right abundance, and it must not have decayed by now. That is a demanding list, and it is worth noticing that dark QCD survives it comfortably, with room to spare. Which raises the fair objection. A theory that survives everything comfortably with room to spare may be a theory that cannot be killed. Ask what would falsify this. The question is not rhetorical, and the honest answer begins with a concession. Dark quantum chromodynamics is not a theory. It is a family of theories, a template with several dials. The number of dark colours, the number of dark flavours, the dark confinement scale, free across many factors of 10. The portal, its type, and its strength. The temperature ratio between the sectors. Fix those and you have a specific model, with specific predictions, which experiments can and do exclude. Leave them free and the framework retreats, and it can retreat a long way, because a confinement scale that can range from an electron volt to a trillion is not a prediction. That is a real weakness, and it should be stated plainly rather than defended. A framework flexible enough to accommodate any result is not by itself science. What rescues it is that the individual models are rigid, and that the framework as a whole makes a small number of statements it cannot take back. Here is the first. If dark matter is composite, its self-interaction is not zero, and it is not constant. It falls with velocity. Measure the self-interaction cross-section in dwarf galaxies, in ordinary galaxies, in groups, and in clusters, across a factor of 30 in speed, and either it varies or it does not. Current data hint. Future surveys, weak lensing across tens of thousands of clusters, and detailed dynamics of the faintest satellites can settle it. A flat, velocity-independent cross-section of zero would not disprove a hidden sector, but it would remove its most distinctive observable signature. Here is the second. If any portal exists at a strength the early universe requires for thermal contact, then dark hadrons are produced in high-energy collisions and some fraction of them decay back to us. Emerging jets and semi-visible jets are not optional. They follow from the premise. Push the collider searches through the full mass range accessible at 13,000 billion electron volts and find nothing, and the portals must be weaker than thermal contact allows, which forces the dark sector to have been populated some other way, and every other way is more contrived. Here is the third, and it is the sharpest, because it concerns the version of the idea where the shadow is literal. The Axion's mass, coupling, and abundance are related by the strong force with almost no freedom. The haloscopes are sweeping the band. If they cover it, from a nano-electron volt to a milli-electron volt, at the sensitivity the theory demands, and hear nothing, the Axion is dead. Not weakened, dead. That is a rare and precious property, and there is a measurement that could kill the Axion tomorrow. Find a neutron electric dipole moment. If the neutron is lopsided at any level, theta is not zero. The Pecci-Quinn mechanism did not relax it, and the entire structure falls. The experiments at the Paul Scherrer Institute, at Oak Ridge, at the Institut Lower Langevin are pushing another factor of 10. Either outcome is decisive. Now turn it around. What would make this undeniable? A composite dark matter signal in a low-threshold detector, showing a form factor rather than a point particle, a velocity-dependent self-interaction confirmed across scales, an emerging jet at the Large Hadron Collider, an axion in a copper cavity at the mass the pions decay constant predicts. Any one of them would be a shadow falling across our own physics, which is what the title was asking about, and it is time to answer it plainly. Hold your hand up again. The weight you feel is almost entirely the strong force at work. 3 quarks in each proton, contributing about 1% of its mass, and around them a field so tightly bound to itself that its energy of confinement is 929 parts in 938 of everything you are. The Higgs field gets the credit in popular accounts. It deserves a percent. The rest of you is a knot in a field, and the field is doing the work of holding the knot. So, is dark matter a shadow of the strong force? In one sense, almost certainly not, and the honest answer has to start there. Dark matter is not made of quarks and gluons. The cosmic microwave background says it does not scatter light, and quarks carry electric charge. The bullet cluster says it barely touches itself. It is not our strong force, and it is not our matter, and no amount of hope changes that. In a second sense, possibly, and this is the idea we've been building. The strong force showed us a mechanism. Take a dimensionless number, let it slide down a logarithm, and it manufactures a mass scale out of nothing. Bind the constituents so completely that none is ever seen alone. What comes out is heavy, neutral, stable, and structured. If the universe used that mechanism twice, in a sector we cannot see, then dark matter's mass would be binding energy just as yours is, and its abundance might be set by an asymmetry counted out alongside the surplus that made protons, and the ratio of 5.4 would stop being a coincidence and start being a consequence. That is dark quantum chromodynamics. It has not been found. It has not been excluded. It predicts dark showers at colliders, self-interaction that softens with speed, and a spectrum rather than a particle. In a third sense, yes, precisely and literally, and this is the possibility that would be strangest of all. The axion, if it exists, gets its mass from our strong force, from the same gluon condensate tunnelling between vacua that makes a proton heavy. The axion would be dark matter whose weight was made by the very field that made yours. Not a copy, the same one. The dark matter in the halo of this galaxy would be an echo of the physics inside your bones, weighing 1/1000th of an electron volt instead of 1 billion because the number that divides it is enormous. That is a shadow in the strict sense of the word, cast by the same object, at the same time, by the same light. Nobody knows which of these is true. It is possible none of them is, that dark matter is something none of these chapters described, and that the answer, when it comes, will make this whole line of thinking look like a beautiful blind alley. Physics is full of those, and they are not wasted. But hold this. For 100 years, we assumed that the visible universe was the ordinary case, and the invisible part must be some simple leftover, a single, dull particle, structureless, doing nothing. It is the majority. It outweighs us 5-1. There is no rule that says the majority of the universe is simpler than the minority, and every time we have looked closely at something in nature, we have found structure. The 5% you're made of took 2,000 years to understand, and it turned out to be quarks, gluons, and a force that makes mass out of its own effort. The 27% is still dark, but if it is built the way we are built, then somewhere out there, in the halo around this galaxy, through which the Earth is moving at 230 kilometers per second right now, there is a second kind of matter, held together by a second strong force, made heavy by its own binding, quietly passing through your hand.